Our oceans are the source of all life on Earth. They regulate the climate, support biodiversity, and feed millions. But today, rising temperatures, acidification, and pollution threaten marine ecosystems around the world. To protect these fragile environments, we need accurate, continuous, and real-time monitoring of the ocean's health. Hi, I'm Max, and in this video, we'll explore how mechanical engineers, chemical engineers, marine biologists work together to design and deploy autonomous ocean health monitoring systems to watch over our world's source of life. In this video, we'll evaluate how buoys are designed from a mechanical engineering perspective, and how sensors are designed from a chemical engineering perspective, and then we'll take the perspective of marine biologists and how they use this data to protect our oceans for future generations. Afterwards, we'll discuss the importance of interdisciplinary collaboration and why it is so vital.
Our first responsibility is structural design. We create the buoy or underwater drone body, making sure it's waterproof, corrosion resistant, and strong enough to withstand storms, waves, and pressure changes. Every component, from the frame to the sensor housings, has to function reliably for months without maintenance. Next, we focus on stability and hydrodynamics. A buoy that tilts too much or a drone that vibrates excessively will distort sensor readings. So we carefully analyze buoyancy, center mass, drag forces, and wave motion to ensure smooth, predictable behavior in the water. Finally, we work closely with chemical engineers and marine biologists to make sure sensors are mounted correctly and protected without interfering with measurements.
My main responsibility is designing the sensing systems that allow the buoy to monitor ocean chemistry in real time. While the mechanical engineer builds the structure, we create the technology that actually collects the data. We start by developing specialized chemical sensors that measure pH, dissolve oxygen, temperature, salinity, and pollutants like oil or nitrates. Each sensor relies on a chemical reaction such as a change in voltage, fluorescence, or conductivity that tells us what is happening in the water. Once deployed, the buoy continuously pulls in seawater across the sensor array. Each sensor converts chemical changes into electrical signals, and our system processes those signals into usable data sent to researchers and marine biologists for interpretation.
When I see changes in dissolved oxygen, for example, I assess whether those levels are low enough to stress fish or potentially create a dead zone. If the pH drops, I evaluate how acidification might impact corals, shell-forming organisms, or key plankton species. And when pollutants show up in the data, I determine how they might accumulate in the food web or affect sensitive marine habitats. I also look for long-term trends. A steady increase in temperature might signal a higher risk of coral bleaching, while recurring spikes in contaminants could indicate an unseen leak or runoff issue. Part of my job is also working directly with the engineering teams. I compare the buoy's readings with field samples to make sure the sensors are accurate, and I help decide where we should deploy these systems so they monitor the habitats that matter most.
As the CEO overseeing this project, what I see is a perfect example of why interdisciplinary teamwork drives real innovation. Our mechanical engineer ensures the buoy and underwater drone are structurally sound, stable, and able to withstand the ocean. Our chemical engineer depends on that platform to deploy highly sensitive sensors that can accurately detect pH, oxygen levels, temperature, and pollutants. And our marine biologist transforms that raw data into meaningful insights about ecosystem health. It's the integration of all three, mechanical design, chemical sensing, and biological interpretation, that creates a powerful and reliable monitoring system. As we deploy this ocean monitoring system, it's essential that we recognize both the benefits and the responsibilities that come with it. Our work has a meaningful impact on society. We provide early warnings that help protect coastal communities, fisheries, and fragile marine ecosystems. These insights give policymakers the information that they need to respond quickly and effectively. But responsible engineering also means anticipating and avoiding potential issues. We design our systems to minimize environmental disturbance, use durable and non-toxic materials, and ensure that the technologies we deploy do not themselves become marine waste. We are equally committed to transparency. The data we collect remains openly accessible to researchers, local communities, and environmental organizations, so that the decisions are grounded in truth, not hidden behind corporate interests.
From an ethical standpoint, we recognize that not all communities are affected equally by ocean degradation. Indigenous and coastal populations often bear the greatest burden. That's why we work to ensure our monitoring tools are equitable and inclusive by collaborating with local groups, sharing data in a culturally appropriate way, and designing dashboards that are accessible, clear, and multilingual. Overall, we hope this video gave some insight on what it is to work on an interdisciplinary team to solve the world's problems in an equitable and sustainable way.